Yes, please enjoy. Anyway, it's a real pleasure to be here. I'd like to thank everyone for coming. Because speaking to an empty room is a little bit difficult. I'm also glad that, I prepared slides, and I hate giving slide lectures, so I'm glad that there are blackboards here and that I'll give a board talk. It might mean that I cover a little bit less, but I don't think that that's ever a problem. I thought at first, so the idea behind this talk was from a really inspiring talk I heard of Gromov's in the 1990s. And the theme was, you only think you know topology, or you only think you understand topology. And I guess the spirit is a little bit something that I read in Feynman's lectures, that what does it mean to, solve an equation? It doesn't, it doesn't necessarily mean solving it analytically. It means that you can describe the properties of the solution and you can answer questions about it, the questions you're interested in, without actually doing a computation. Okay, so one of the big, so high-dimensional topology is in some ways been a very successful field in the last century. In the current century, I think the main problems have to do with the interaction of the fundamental group and global properties of manifolds. But it's there's sort of a well-defined paradigm where people will start off with a geometric problem and they will translate it into an algebraic topology problem, maybe mixed with algebraic K-theory or quadratic form theory or something or other, some pieces of algebra. Okay? Sometimes this involves many, many steps. Then they farm it out to the algebraists. The algebraists go ahead and solve the problem. And then the geometric topologists say that they solve the problem. And the question is, and you can revel in this. You could think that this is really wonderful. So for example, maybe the first example I think of this was when Shmuel showed that you could invert the two-sphere, right? That you could turn the two-sphere inside out, right? So that there's a one-parameter family of immersions of the two-sphere, one of which is the standard one, the other one is where you flip it, right? You change the orientation. And the proof of it is because pi2 of an orthogonal group is 0. And that's the proof. And you then say, okay, it's wonderful, Mr. Shmuel. And, that isn't actually his reception. His advisor was Bot, and Bot said, that's ridiculous, it can't be true. And then he had to follow the proof line by line in order to follow it. But I think Gromov's point was that, you go ahead and you prove a theorem, some homotopy group is 0, so therefore two elements are the same. Doesn't take an additional calculation at that point. Okay, and so you could invert the sphere, and the question is, all right, so that's fine as far as it goes. It's like going to the Delphic Oracle, asking a question, maybe a little better because the Delphic Oracle there were always questions of interpretation. Okay, and here the answer, yes, it really is the case that you can, regularly homotop one to the other. But if you want to understand, if you ask the question because you were really interested in understanding something, then maybe just having an oracle tell you yes or no is not good enough. Okay? So, okay, so that was the problem. So of course, in the case of sphere eversion, there are now movies, right? That go ahead and show it, and it's quite non-trivial. Okay, and but more generally, the question is, what about this whole process, right? People worked years before they were able to go ahead and, produce the sphere eversion movies. So the question is, in general, this process where you take something geometric, you replace it by something algebraic, then you go ahead and do the algebra by some kind of crazy method, right? You'll do an atom spectral sequence or something like that. Do you know anything? So those were the problems that Gromov asked. And so I heard this talk in the 1990s. It was based on actually things that he had been thinking about for the previous 20 years. And so what I want to do is I'm going to describe one particular problem that Gromov called attention to at that time, not the one about immersions. A lot of the same ideas that I'm going to talk about, much of what I say is really based on the idea that this is a paradigm rather than this specific problem, but I think it's better to talk about something specific than engage in too much generality, okay? Which I think I've already spent 5 minutes without putting anything on the blackboard, so maybe that's enough generalities. So the problem that I want to talk about is the Cobordism problem. Okay, so you have M, which is a compact, smooth manifold. And the question is, does there exist a W? Okay, so M will be M-dimensional, and W will be M plus 1 dimensional, which should also be a compact, smooth manifold. This one is closed. And this one has with boundary W equal to M. Okay, right? So this is the Cobordism question, okay? And so in dimension 0, for example, 2 points are the boundary of an interval, okay? If we're working unoriented, oriented, then you have, these points are oriented oppositely, whatever that means, okay? And, so I think we know about Bordism in dimension 0, okay? In dimension 1, the only compact manifold is a circle. The circle bounds a disk, okay? So that's the Cobordism question. And René Thom answered this. Let me just, before telling you his answer, I just want to mention why this is an important problem. Firstly, I mentioned already one reason, that it's a prototype. That this problem is after immersions, I think it was the next problem that got reduced to algebraic topology and got solved that way. Cobordism is sort of important for the following reason. If I have a map between smooth manifolds, okay, I know X and Y are not usually the letters for such things. Okay, if you take if I take the inverse image of a submanifold, okay, generically I'll get a submanifold. Okay, if I might have to perturb the map. Okay, but if I perturb the map in 2 different ways, obviously I'm going to get a different submanifold, and the different submanifolds I get might not be diffeomorphic. Okay, especially if initially I had to perturb it, right? If it was a singular fiber, so to speak, right? Then when I perturb it, I'll get one version. If I perturb it a different way, I'll get some other guy, and then by looking at the one parameter family that interpolates between the 2 perturbations, okay, then you'll get a cobordism between them. Okay, so these manifolds also have different flavors. So then you get involved in different flavors of cobordism, right? So you could also talk about, the one that René Thom solved was unoriented. You could look at oriented. You could look at complex. You could study PL, okay? Right, there are many, many flavors, and all of these have utility, okay? Okay, so also cobordism turns out to be related to many other problems, like in geometric analysis. The first proof of the T-Singer index theorem went by way of cobordism methods. Okay, so also Bordism, instead of just asking about M, you could jazz it up. You could look at M with a map to an auxiliary space, and then you could ask about extending it over here, and then you get a homology theory, which is extremely useful, okay? And that furthermore, when you look at this theory, it automatically has tautologous characteristic classes. Like you could look at M with the identity map to M, Okay, and in that homology, that was the easiest thing in the world to define, right? But of course now you've moved all the difficulty to understanding that homology theory. Okay, and people know that understanding a homology theory, the hardest part is understanding the homology theory for a point. I mean, in some sense. Okay, so this is overall extremely fundamental. And then there's yet another reason, which will play a role later in the talk. And that's an idea that goes back to Atiyah, Patodi, and Singer in the analytic setting. It goes back to Wall and Hertzebruch in more topological settings. And the basic idea is this. If you're going to be, say, comparing things, right, from the point of view of that homology theory that we were just discussing, okay, suppose, right, so the first thing that you compute is, do these characteristic classes agree? So, what? Yes, so M is the target, right? So I was talking about that. A way to study a manifold is to consider the identity map as a cycle in this theory. Okay, now I have another manifold that has a map to it, and I want to know whether this other, the extent to which this other manifold resembles M. Okay, right? So the first thing to do is to compare this tautologous class to this less tautologous class. Okay, and allegedly, if you understood what René Thom told you, right, then you would compute that they're equal, because if they were unequal, your problem is done, right? You don't have to compare them anymore, perhaps, right? Right. So then, thanks to Thom, you get a W. Okay, and now the next part of the idea is that a secondary invariant. Oh, I'm giving you a sort of a. Oh, okay. You're wanting me to not bullshit as much as is my inclination. No, it's okay. I'm not criticizing. Yeah, no. So for one, so I mean, again, I'm trying to give a schema here rather than a specific thing. But for example, in surgery theory, the M prime would be homotopy equivalent to M. Okay, and then you would firstly try to produce such a cobordism, and then afterward you try to turn the cobordism into an H cobordism, and then you might learn that M and M prime are diffeomorphic under some fundamental group conditions. Okay, right? That would be a way in which this would be used. Okay, but there are other places where M prime to M has weaker features, and and you would use this for some other reason. But the basic point is that in this process, where you actually want to make use of René Thom's work, the next step is you produce a W, and then a secondary invariant of M prime to M would be some invariant of W. So then you have to, of course, study to what extent the different W's give you the same answer. Okay? That's obviously part of doing the mathematics of this program. But in terms of using the program, you have to be able to find the W. Okay, so if you can't find the W, okay, then then you're stuck. Okay, so Atiyah, Patodi, and Singer. So in the case of Atiyah, Patodi, and Singer, the invariant that they were interested in was the signature of this manifold. Okay, and then what they showed was that this secondary invariant, they managed to find it without finding the W at all. They discovered that, for signature of W, they found an expression that's called the eta invariant, which is a spectral invariant. Okay? So it turned out to be definable intrinsically in terms of the manifold. So that was sort of a wonderful, maybe, hint to the program, because even though we had no way of understanding the W, because René Thom's stuff is completely inexplicit, there are things about W you could measure from the manifold M. Okay? So, okay. All right, and yeah, so I'll maybe return to the theme. Oh, I have another blackboard I don't need to erase yet, but I do need to look at my notes. Okay. All right, so let me now maybe return to what René Thom proved, and then I'll tell you what Gromov asked about that solution, and then I'll probably have to look at my index card again. Okay, so here's what René Thom proved. Okay, and what he said is this: you look at your manifold. You embed it, so I'll just draw a picture. You embed it in some high dimensional Euclidean space, say R2M plus 3, say. Whitney plus a drop more room, don't want to tell you why. Okay. Now you consider the Gauss map, so that at every point of the manifold, you look at the tangent space of the manifold at that point. Okay. So, which lives in some Grassmannian of M planes in 2M plus 3 space. Okay? So far, so good? Okay? So then this gives you a class in the mth homology of this Grassmannian. Okay? Homology of Grassmannians are happily classically understood. And René Thom's, one of his theorems is that M is a boundary. Well, an obviously necessary condition is that this should be 0, right? Because after all, if M bounded something, right, then the thing that it bounds would also have a Gauss map, okay? And I am suppressing one technical point, which hopefully no one will ask me about, okay? Right, and then that would give me a chain that bounds this cycle. Okay? And René Thom's theorem is that this is necessary and sufficient. Okay, and the work on oriented cobordism says that for oriented manifolds, the same thing is true. Okay, and for other flavors, no, it's not that simple. Okay, you can't just phrase it homologically in terms of Grassmannians. Okay, but the method that René Thom used is suitable for the problem. Okay, so, okay, beautiful theorem, right? So if you're giving me a manifold, right, I just go ahead and I look at, there's something or other I have to compute, right? So I do the calculation, I get 0, so then there is this W that René Thom gave me. And now the question is, so Gromov's question is, how complicated is W? Okay, so let me elaborate on this. So, given M, I'm going to give it a Riemannian metric. Okay, right? Contractible space of Riemannian metrics doesn't bother me at all. Okay, and now Gromov points out, we could say that the complexity of Mg, so I don't want to write down a formal definition. Let me just say, assume that the curvature, all the sectional curvatures are bounded by 1, and that the injectivity radius of Mg is bounded from below by 1. Okay, this is an entirely safe thing. If I have any Riemannian metric at all, I could just rescale it, right? When I multiply by a constant, the curvature gets divided by the constant squared, so I'm lowering it. The injectivity radius gets multiplied by the constant, so that gets bigger. These are not in any tension at all. Completely achievable, right? Okay, there's no harm at all in assuming this. This space of Riemannian metrics is also contractible, right? So this is almost nothing. And then we'll say that the complexity of Mg is just the volume. That's how we'll measure complexity. Okay? And why does that make sense? Because the volume is rough. When you say something like this, the space of metrics on the ball is a pre-compact space of metrics. So, right, so the balls are pretty much standardized. And then the volume is saying how many balls you have. Okay? So, for example, if you know this complexity, the number of diffeomorphism types is bounded above and below by exponentials in V log V. Obviously, the base of these exponentials are different, okay? In dimension 2, there are fewer of them, okay, right? That's this amazing classification of surfaces. The volume will be about the genus, right? I mean, in dimension 2, but in higher dimensions, you know, this is what happens, right? So for people who are used to thinking about three manifolds and thinking that the hyperbolic structure is the one that you want to look, here you're going to have to change the curvature a bit if you were to be like filling a cusp. Okay, but anyway, this, you know, so this is a notion of complexity. If I tell you complexity 5, it's slightly super exponential in that number 5. Okay, and there are only so many manifolds. Okay, so a priori, so now here was Gromov's question. So if I'm given mg and I'm even given the complexity, I'm going to call it just v of m, right? So given v of m and that there exists a w such that m is the boundary of w, right? Because that's the question that René Thom answered. When can you find such a w? The question is, what is the inf of the volume of w such that boundary w equals m? Okay? Right, so if your manifold isn't that complicated, is the thing that it bounds necessarily, you know, is it going to be way more complicated or not? Okay? So you understand the philosophy of the question, okay? And what I want to spend the rest of the talk on is understanding the question. Okay? And for W, assume maybe that you have a collar of some size near the boundary. I don't want to do anything fancy, and that W has the same conditions as M. All right? Right? I mean, you know, we're not trying to do anything fancy. We're just trying to ask, if your thing has only so many coordinate charts, how many coordinate charts would you need for the thing that it bounds? Okay? So René Thom's proof, by the way, was entirely non-constructive. Gromov didn't quite give a proof of an assertion, but he did make an assertion, which was something like 2 to the 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 v, where this thing was dimension -2. And he sketched the proof, and his sketch proof is plausible enough. I don't actually know anyone who's filled in the sketch proof, but I have no reason to doubt it. Okay, okay? And so this was, of course, a big step forward, you know, going from completely ineffective to a tower of exponentials. You could imagine how it goes, that there's some inductive step depending on dimension, and that whenever you do the inductive step, it costs you an exponential. Okay? You know, that was the philosophy of his argument. And then in typical Gromov, the word I want to use is chutzpah. I don't know if everyone here knows that word, but if you don't know it, maybe you should think of this conjecture as being an example of it, which is, so the conjecture of Gromov is that linear is true. Okay? That you don't need this tower, right? That you know, there's just, the size of W should just be something like the size of M. Okay? And it's a great conjecture. You could, I don't know, it lit up my imagination, you know, when I heard it, you know, over 30 years ago, and, you know, for a decade or so, I put it in my NSF proposal, but I never made any progress on it. So I had to take it out of my proposal, but I couldn't take it out of my mind. Because it really comes to the question about what the hell are you doing when you're doing topology, right? I mean, do you understand anything? So let's see, I think, so there were sort of two reasons why Gromov asserted linearity. The first one was just, he couldn't believe that the algebraic topologists were that smart, right? I mean, if it was going to, you know, if somehow, you know, you go to the Delphic oracle and it tells you something exists that's that big, that's just shocking. And maybe the Delphic oracle could do it, but like, you know, he didn't believe that algebraic topologists, you know, could be doing something like that. Okay? That sort of, you know, general philosophical thing. That one would have given you maybe weaker conjectures that might have made you believe that it's polynomial, by the way, right? How much do you have to disrespect algebraic topologists? Okay, right? That's an open problem, okay, that I'm not going to discuss. The other reason that Gromov had was the clue was this theorem of a Tia-Petodian singer. So therefore, lots of signature-related invariants of manifolds, which are, incredibly important in many investigations. And Cheeger and Gromov proved that, for a whole family of these, I'll just put a little row at the bottom, where row is some additional representation somewhere or other, that all of these things are linearly bounded in the complexity of M. So the natural explanation would be, right? So if I have a W, right? So if we're in this situation, the complexity bounds the number of cells, right, in the cell decomposition. So therefore, it would also bound the signature, right? Because the Betty numbers will bound the signature of a quadratic form that's based on them. So the only, the geometric explanation for why you would be able to prove an analytic estimate on eta invariance would be if you had linearity. So I think that was what pushed Gromov to make the conjecture beyond polynomial to go to the setting of to suggest even linearity, because that would have been a beautiful explanation of this analytic estimate, which they did by spectral geometry. Okay. Yes and no. Okay, so I love that question, and I will therefore address it. And that way I will have, a perfect excuse for why I don't get through what I was planning to. So if you would ask about something else, right, like how many handles in a handle decomposition, okay, then that is not directly related to this, because there are infinitely many manifolds with a given handle complexity. In dimension 3, that complexity is the Heegaard genus. Okay? So, so Leray covers and handles and things like that, that doesn't capture it. Okay? On the other hand, you could ask, say, let's triangulate our manifold and ask for how many simplices are in the triangulation. Now that's a very good complexity notion, because again, if you have bounded complexity, there are only finitely many possibilities, and here it's almost tautologous, right? Because even if you get your simplices in the mail from Amazon, and and they include the directions on how to put your manifold together, and then you lose the directions, you just keep trying, and ultimately you'll get your manifold, right? And that more or less is the same thing with one proviso. Here we have these kind of local conditions on the injectivity radius and the curvature, and that boils down to saying that you want your triangulation to have a bound on how many vertices neighbor a given vertex. So that you would call to maybe a locally bounded complexity PL manifold. So if you were to put on a bound in local complexity, then that PL complexity will boil down to this Riemannian complexity, with some constants. Those constants turn out to be ineffective, and necessarily ineffective, because it's undecidable in high dimensions. If I give you something that I claim is a triangulation of a manifold, so it might have a homology sphere and that I've taken the cone on it, and I don't know if that homology sphere is simply connected or not, so I don't know if I really had a PL manifold. So if I could turn it into a smooth manifold, it would definitely be a PL manifold, and so on and so forth. So there are constants going back and forth, but they're ineffective constants. Okay, another issue that gets hidden away in some of the things that we're discussing. Okay, so in the PL version, there are sort of two different versions of every question. There's the version with bounded local complexity and the version without bounded local complexity. And frequently one problem or the other is much, much easier than the other. By which I mean one is known and the other is not. But unfortunately, sometimes it's the bounded complexity version that's known, and sometimes it's the no condition at all on the neighborhood. So PL is in a much weirder shape than the smooth theory. Anyway, so okay. So rather than, I'm going to now like ruin the suspense. I was going to build up to what it was, but I fear that I won't get, near where I should be getting, so I should at least state a theorem. And this is based on earlier work of Chambers, Dotterer, Manin, and myself. And the theorem is that for all epsilon, there exists a W such that the volume of W is less than some constant that depends on the dimension, and it depends on epsilon, v to the 1 plus epsilon. So slightly superlinear. So that's what the theorem says. With Chambers and Dotterer, it appears in the same paper. This thing here is in an appendix to the paper. The main result of the paper does this, where here you have the volume to some, it's a polynomial in volume, but the degree of the polynomial was exponential in the dimension. So there was one set of ideas that reduce things to polynomials, and then there's a completely orthogonal set of ideas that reduce the polynomial down to slightly superlinear. And I want to focus on the first part, because the first part is the part that has more universal application to other problems, like to immersions and things like that. Or to surgery theory. So anyway, it's like it's close to Gromov's conjecture. I have to say so I worked on this for more than 20 years, and I didn't expect to get this. My dream was to get it down to a tower of 2 exponentials. All of these people are much younger than me and much more energetic and smarter, and they didn't work on it 20 years, so they didn't go down as many false paths, and they really put me in my place. I'm grateful to all of them. Let me just comment that I don't believe Gromov's conjecture. And I think that's, given that this is an audience of people who are also mainly younger than me, I want to just point out why it should be false, but I don't know how to make an argument. Why should linear be false? Now, by the way, when you get it down from a tower of exponentials to something like this, you could say that you proved Gromov's conjecture. That would be fair. Because again, I thought he was, I believe that it was wrong anyway. I couldn't believe, I thought I might get it down to 2 exponentials, that the truth was polynomial of some high degree. That was what I thought, that's what I thought the situation was. But now I should tell you why I think it's false. And Gromov, I think it's fair. If it's false, then, again, it doesn't really matter. And here's the idea. I mean, it should be false already in dimension 2. Okay, and why is that? Okay, we all know what surfaces are. Okay, and they all look, right, sort of like this, right? They look like bagels with, pretzels with many handles. And those, of course, are very easy to fill in, right? But if you think about surfaces geometrically, right, well, you know that they're actually very, very complicated. Like, think about three-valent graphs, right? They're all homotopy equivalent to a bouquet of circles. And, I mean, there are lots of boring three-valent graphs, but your random three-valent graph, is going to be an expander. Okay, and it's not so rare, right, that a three-valent graph has large girth. So the same thing is true for surfaces. So if I have volume V, the shortest closed curve that's non-trivial, right? So the way we null cobord this, obviously, right, not by the proof of René-Thom's theorem. The proof of René-Thom's theorem, gets you this, and we don't want to go there, right? And for surfaces, we shouldn't have to do that. Okay, so of course you could use the classification of surfaces and make all your surfaces into these boring pretzels. Okay, that's offensive, right? So we want to deal with the surface as it's given to us. And if you're given the surface as it's given to you, the shortest closed curve you expect is about log V. Okay, now what do we do with such a thing? We cut open, and then we fill this in with a disk, right? You do the surgeries. And how many surgeries do you need to do? You need to do the genus. And the genus is about V. So if you were to give me an expander-like surface, right? Say, or I got one from Selberg or somebody, right? Why in the world should it bound a 3-manifold that has volume that's linear in V? Okay? I don't know how to prove it doesn't, but maybe one of you will. Okay? It's something that I've been thinking about for a long time. That's not evidence that it's hard. Just, I need some young people to set me straight. Yeah, okay, right. The obvious way to take a surface and make it bound to 3-manifold is you do surgery on some collection of curves, right? If I have a, right, so we know that systoles of a hyperbolic surface, they tend to be around log of the genus, or log of the volume, right? So that puts this, but then you have to do G surgeries. So that should be a V log V, which is, morally it's correct. A logarithmic correction is something that I wouldn't hold anybody to, but they're an evidence of some amount of depth. Okay? So anyway, so I want to, I'd like to advertise this problem. Even in dimension 2 is Gromov's original version correct. And the only reason that I'm making an emphasis about it is because this linearity was suggested by the Cheeger-Gromov heuristic, right? That really was a linearity thing, right? So, so it's a matter of, how much does one believe the Cheeger-Gromov heuristic? Yeah, Goliang. Yeah, right. I want to imagine a surface of large, concretely, take some compact arithmetic surface and then take the congruence covers, and those should provide a counterexample, I would think. Yeah.
So I guess the issue with this heuristic is that you take the surface and you take the metric on the surface that is that.
No, I think no, that's such a beautiful metric. No one could think that that's a bad metric. No, for one thing is, Gromov, you could be a little bit slippery and say, oh, well, by the complexity of a manifold, I want you to inf over all metrics. But, that's one version of the conjecture. But you could have also said, I just start off with a Riemannian metric, and I want to find this Riemannian W that it bounds. Okay, and then you don't have to inf over metrics. One of the reasons why I prefer the second one is that, firstly, it feels more natural. Also, the version, where you inf over metrics gives you an invariant that's not computable in the sense of recursive function theory, for similar reasons to what I was explaining about not being able to tell whether a manifold is a PL whether a polyhedron is a PL manifold. Okay, so so like this, it's a measurement you take rather than something that you try to compute. Okay, so yeah, no. So of course the hard part is that I gave you some description of how to make a manifold bounded 3 manifold, but maybe there'll be one that exists for a much more subtle reason, and then that would be a fantastic thing to know, I think. Okay. Okay. Yeah, so let me sketch a little bit about what goes into this. Okay, and okay. So the first thing is that you have to take M and you have to embed it into this high-dimensional sphere. Okay, that is an act of violence. Okay, and I'm not going to say anything about that step, but that was in fact what is the difference between this one and that one. Okay, what you want to do is you want to take your manifold and embed it in the sphere so that M is not so distorted. Okay? Okay? And the subject of metric embeddings is an enormous literature. Some in the theoretical computer science literature, papers of Bergen, Matuszek, Asaf Naor. And so it turns out that what we do is we use some techniques that Gromov and Guth did for embedding polyhedra, which is some kind of 2-scale embedding thing. But the upshot of this is that you can't make it necessarily by Lipschitz to what you had to begin with, but let's ignore that and let's just start off with an M that is nicely embedded. And by nicely embedded, what should that mean? Firstly, it means that the normal exponentials shouldn't collide too soon. Okay? Right? I mean, right? And then there's, and that, so that's sort of a global condition. I drew it over here. Over here, of course, global exponentials, those exponentials will collide for another reason, which is the curvature reason. Okay, but here we assume that the curvature was bounded. So again, we want to, that's sort of the main feature about it. And now if you think about it, this thing about to say that the normals are, not moving very much or whatever, I mean, this is very much related to, okay, so let me introduce one of the dramatis personae in this proof. There's a map from this to something that's called the Tom space. Okay, and this is what the Tom space is. Here we have the Grassmannian. Okay, over here I have the M+3 planes into M+3. Okay, it turns out you want to look at the normal directions instead of the tangential directions. Okay, that's one subtlety. That was already there in René Thom, but it wasn't there in the way I explained Thom's work. The point, okay, the condition about curvature is saying that restricted to the manifold, right? So the map that we get is defined like this. There's a little tubular neighborhood of the manifold. Okay, so so over here we're going to look at the normal direction. Okay, and now we have this little tubular neighborhood. So every point in that tubular neighborhood has a base point, so it goes to a point on the Grassmannian, and then it has a normal direction in the disk, so that will give me a point in the unit disk of the tautological bundle. Okay, and now even though this thing here is tiny, rescale to go to the disk of size 1. Okay, because I have to be going to some specific place. Okay, so then I have the disk bundle over the Grassmannian. Now, take this disk and identify the boundary sphere. Identify that with a point. Okay, an act of violence. Okay, but this is still a nice compact polyhedron after you've done that. Okay, and so firstly we have a map from the tubular neighborhood to this, but on the boundary of the tubular neighborhood, it's going to that point star. Okay, and you just map the outside of the tubular neighborhood to star. Okay, so this is called the Thom map, and the piece of algebraic topology that René Thom proved was that this map from the sphere to the Thom space is homotopic to a constant if and only if it's zero in homology. And the condition on that zero in homology, by the way, he proved the Thom isomorphism theorem in order to prove this. And he also invented transversality to do another part of the argument. It's a really breathtaking paper. He deserved his Fields Medal. Okay, so right, so you get what the map is, and now the kind of conditions. So what I claim is that so here we have a map which I'll call phi sub m, right? So m is embedded in the sphere. We have this map. Okay, now how does m relate to this map? It's the transverse inverse image of the Grassmannian, of the zero section of that bundle. Okay? Okay, and the point is that the Lipschitz constant of phi is related to the volume. Okay, under these kind of conditions. It's going to be a volume to some power. Okay, let's not worry about that. Okay, I mean, it's something that one has to worry about when you're proving the theorem, but let's not worry about it right now. Okay, it's clear, right? I mean, the Lipschitz constant along M, right? That's how are these tangent planes moving, right? That's obviously a curvature condition, right? When these things get close to each other, right? That's forcing this tubular neighborhood to be skinny. And then I have to rescale it to be a unit disk, right? Because this I want it to be a specific compact polyhedron so that I can talk about the Lipschitz constant, right? I mean, so I better fix the metric. So, right, so the skinniness of this tubular neighborhood is the other aspect of the Lipschitz constant, okay? Okay, and then there's a matter of just analyzing what's going on, right? If you have good embedding, blah, 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 okay? And now, if I had a null homotopy, if this extended to, say, B2m plus 4 mapping into here, that would be a null homotopy. I would take the transverse inverse image, right? I call that capital phi. Then I would take capital phi inverse of the Grassmannian, and that would be the thing that it bounds. Okay? Right? So are we all happy? Okay, are we now all unhappy? Right, because this is its great mystery, right? You're going to the, I just translated one impossible problem to a different impossible problem, right? I have a map that happens to be null homotopic, but I need to have the null homotopy in order to produce the null cobordism. Right? Algebraic topology is some miraculous tool for saying, right, a null homotopy exists. Oh, that's exactly equivalent to saying that you're equal to 0. Okay, so it means that something or other gets hit by something and right? You don't know what the hell you're talking about, right? So in order to deal with these problems, one has to deal with some kind of quantitative algebraic topology. Okay, so this is a subject that has been developing in the past 10, 15 years. So the first theorem in this subject is if x and y are simply connected, then the number of homotopy classes from x to y with Lipschitz constant less than L is O of L to some power. Okay, that was sort of the first theorem in this general area, and that was a theorem in a paper of Gromov from the 1970s, and then in the 1990s he said it was a conjecture. But in a 2020 paper of Fedya and mine, we filled in all the details. And I mean, you know, Gromov has great geometric and analytic insight. As an algebraist, he's not perfect, and it turns out that there are some algebraic difficulties and also a geometric difficulty, one that he missed because he was relying on Sullivan. The proof of this is by rational homotopy theory. Okay, and it's sort of the beginning of, and all of this quantitative algebraic topology gets deeply connected to rational homotopy theory. So this was the, X and Y are finite complexes. Okay. So in order to prove this, you need to do something or other about minimal models. That's algebra, so we don't blame Gromov. Okay, I mean, but he basically saw what the point was. The thing that was a little bit missing is that there's a theorem of Sullivan that there are only finitely many homotopy classes in any particular rational homotopy class. The trouble is that that's not a uniform bound. So the minimal models would give you this estimate, but then each point might have some additional, some growing number of particular maps. But it turns out that that growing number can also be bounded in terms of the Lipschitz constant. So this shows that there is a subject. Okay? And by the way, if X and Y are finite complexes, and you know the Lipschitz constant, it's easy to see. You can just use our Zela-Ascoli to tell you that there are finitely many homotopy classes. And you could again you don't have to be Gromov, you could just be a numerical analyst, and you could get an estimate on how many there are. And it's O of exponential of L to the dimension of X. And that estimate turns out to be the correct one when Y is non-simply connected. Okay? So without some non-trivial algebra, so this is an amazing thing. Algebraic topology turns this kind of crazy super exponential estimate into a polynomial estimate. Okay? And somehow that's the core of the mystery, of the subject. So anyway, so this is a theorem of Gromov. I'll tell you an intermediate theorem that Steve Ferry and I proved. I think in the early 2000s, it says the following are equivalent for a space Y. The first one is that if F and G mapping X to Y are homotopic L Lipschitz maps, then there exists a C that just depends on the dimension of X times L Lipschitz homotopy between them. Right? This would be the algebraic topology analog of Gromov's question. Right? You're thinking about the Lipschitz constant, and it says that when things are homotopic, right, when the algebraic topologists tell you something, you could just turn it into, just increase the Lipschitz constant some amount. Okay? But I'm saying that not only, it also doesn't really depend so much on the polyhedron X, it just depends on the dimension. Okay? I'm adding that extra refinement to the conjecture, which Gromov didn't ask for. Okay? And the second thing is that the homotopy groups of Y are finite. Okay? So this excited me when we proved it. It turns out to have applications to the Novikov conjecture and things like that. So, it's not completely useless. It also is related to Gromov's original question for unoriented cobordism, because if you take any manifold, 2 times it bounds it cross an interval, so all the homotopy groups are Z2 vector spaces. That's pretty close to showing that the homotopy groups of that Tom space are finite. Okay, so
I have another question.
part, but also the torsion part, right?
Yeah, everything is finite.
Is Y assumed to be simply connected or not?
No, not in this theorem. For a lot of the in Gromov theorem they were, but if it's finite, you see, then it's not. If a space has finite fundamental group, then you actually know what it is. There are no secrets about that, and then you could look at the universal cover, and then you're simply connected, and then you could just do everything you wanted to do before. So that turned out not to make a difference. So for unoriented cobordism, this would be enough to explain the theorem. I mean, Ferry and I didn't do the hard work of figuring out what estimates you would get, so that was why I thought it was two exponentials. And the kids explained to me that it would be actually polynomial, and then with that, et cetera, et cetera. So this would be enough for unoriented, okay? But for oriented, right, we know a point, no multiple of a point bounds, right? So all the homotopy groups, that come up in cobordism, they're all infinite groups. So this theorem gives you some optimism about the unoriented case, but it's self-defeating, right? I mean, it doesn't enable you to do anything about the other cobordism theories. Okay, so good news and bad news. It did not escape anyone's attention that this hypothesis is, roughly speaking, saying that something has the rational homotopy type of a point. Okay, ignoring problems of nilpotent, blah, blah, blah. But, okay, so one knew that rational homotopy theory should be entering into the general theory. So let me just, So it's a pity, I won't get to explain the ideas and the proof of this, but maybe I'll say a little bit about the further directions. So this is the theorem that Chambers, Dotterer, Manin, and I proved, which is that if the cohomology of Y with coefficients in the rationals is free as an algebra, okay? So say it's just, imagine that Y rationally looks like a product of odd spheres, okay? But you could also handle like CPNs and things like that. So all the Y's that are H spaces, so for many problems in topology, the algebraic topology that you're dealing with satisfies this condition, okay? Immersion theory is one of the situations which doesn't, by the way, okay, right? So I'm glad I'm not talking about that today, okay? Then the theorem is that for all x finite, there exists a C of x such that if f and g map x to y are homotopic and L Lipschitz, then they are C of x, L Lipschitz, homotopic. Okay, so that what happens is you still have the same kind of theorem that Ferry and I had, but it depends on the domain. Okay, and unfortunately I can't explain the geometry about that because I only have 2 minutes left. So let me just say that since then there have been many other Y's that we've been understanding, and I wanted to explain a wonderful thing that Manin discovered called the shadowing principle, which turns out to be that if you have a map and you want to know what the best Lipschitz constant you could that there is for that map, up to a multiplicative constant, it's determined by finding differential forms on X that are predicted by the map being L Lipschitz. That if you could find so if the target was a sphere, right, there's just one differential form. If it's an odd dimensional sphere, and that was what was occurred in this theorem, for an even dimensional sphere, according to rational homotopy theory, the even-dimensional sphere has sort of two generators in its minimal model, so you really need to have, sort of two differential forms with particular properties. Okay? So the analog, so Manin's work reduces these things to finding suitable differential forms, but it turns out that these kind of problems about differential forms are extremely subtle, and they're not so easily predicted by rational homotopy theory. And the most beautiful recent development in this direction is a paper of Berdnikov, Larry Guth, and Manin that gives sort of polylogarithmic corrections to what you would expect from rational homotopy theory based on harmonic analysis. Okay, so there's a whole beautiful subject about this for various complicated target Ys. But for most of the problems that occur in, say, surgery theory or Cobordism or things like that, this theorem suffices. Okay? I'll just say that if I cared about the PL version, then there isn't there is a reduction to algebraic topology, but it's not a compact polyhedron that you have here. So the whole framework falls apart. But nevertheless, with bounded geometry, it turns out that one can still prove analogous theorems. So so that's one of the mysteries about the role of bounded geometry that Edward sort of implicitly raised. Comes up when you want to try to prove the PL version because you don't map into a compact polyhedron, so I don't know what I mean by a Lipschitz function, right? So it sounds like the whole program falls apart. But Manin and I have a preprint that explains what you do for bounded geometry, but we have no clue about the PL version with unbounded geometry. So for bounded geometry, we again have the theorem with a v to the 1 plus epsilon result. Anyway, I better stop because I could go on for the remaining 2 weeks, week and a half, whatever, so I better stop.
Thanks a lot for the beautiful talk. Are there any further questions?
I have several questions.
Yeah.
Can you follow the statement of your theorem with Ferry? That test out y infinite. So does that mean it has no free part or?
Yeah, it means no free part. Yeah, so like the suspension of RP2. Okay, that would be an example. Or unoriented Grassmannians.
Okay, yeah. Thank you. Then for the Gromov.
No, I mean unoriented Tom spaces.
Then for the Gromov theorem, since it uses the minimal model, so it's hard to generalize for the general non-simply connected cases.
Right. So it's not true, right? This is the thing that's true.
Oh.
Okay? I think if you look at pi n of the n torus wedge the n sphere, this grows like exponential in L to the n. Okay? Right, so.
Yeah, the remaining question may be very nice. So first, you mentioned in the beginning that when if you use for complex geometry, when M is a complex, what's the requirement of complex? When M is a complex, what's the requirement for W?
I mean, that's in Quillen's calculation of complex cobordism. I mean, I don't remember. Usually these people will phrase things, they focus on what the whole cobordism group is, and then, Quillen's calculation is that it's a Lazard ring or something like that. So, I mean, usually that's the way it translates. But in the case of Bordism, rather than stating it that way, I like this way better, and for example, for PL, it's just that there's an algorithm. I mean, one doesn't really know what the criterion is. What you just say, associated to the PL manifold, there is a map into a space that's basically produced by the Brown representation theorem. Something or other is a representable functor, so blah, 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 there exists a space, blah, 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 homotopy group, blah, 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 and a class is 0. Okay, right? It's really, it's like you have to pay so much before you even get into the oracle to ask the question. But, yeah. Yeah. No. I mean, we could do better than that. I mean, we have some corrections, but I mean, I don't remember what they are. So, by the way, let me tell you where some of it comes from. So, firstly, there is distortion when you try to embed a manifold into a particular sphere. And the distortion goes down when the dimension of the sphere goes up. On the other hand, when the dimension of the sphere goes up and I look at a transverse inverse image, the complexity of the inverse image goes up as well. So there's a tension, okay? And that, and that somehow the fact that something or other is n-dimensional and the cobordism is n plus 1 dimensional, you never get a thing where those things are matching up. So our methods, yeah, so I don't think that so you could optimize exactly which dimensional sphere you go into associated to what the complexity of the manifold was, and then you could improve the 1 plus epsilon to some specific function but it's kind of gross, and I forget whether or not we wrote it down in our paper. I mean, we certainly wrote it down on scrap paper, but it's nothing that I want to talk about.